Hello everybody, I am Dr. Sreedevi, Assistant Professor, IARE, Hyderabad. Today in this session of graph theory, we are going to discuss matching. We will see what is matching. Before going to the formal definition of matching, now we will see some real life applications from where and how this matching has been started to learn as a different area in graph theory. Okay. Now, starting with one real life situation, it happened in 1941. In the Battle of Britain, Royal Air Force consisted of airplanes having two pilots. That is, British Air Force had two planes having two pilots. However, certain pilots could not fly together because of the language difference or training difference or something, or some other reasons. The problem is with these restrictions. That is, every plane has to be flown with two pilots, and with this, everyone cannot be put into the same flight. So with this restriction, what is the greatest number of planes that can be airborne simultaneously? That is, if we are selecting a pilot and if X and Y, sometimes they may not be able to fly with together. So what is, with these restrictions, there may be a certain number of pilots, there may be a certain number of flights, and with this restriction, how many flights can be? These certain pilots may not be able to fly together, and with this restriction, how many flights can be airborne simultaneously? That was the problem. Another problem then came across was in a co-education institution, each girl has R boyfriends and each boy has R girlfriends. The problem is in a dancing program. Is it possible to conduct a dance where all the students simultaneously dance with their friends? This means if one girl is selected, then she has to dance with a boy who is a friend of her. In the same way, if a boy is selected, he has to dance with a friend of girl who is his friend. That these problems gives rise to these problems, and similar problems can be solved graph theoretically using the concept of matching. You all know matching means some kind of assignment. You see, since the problem of matching or assignment, here we are taking this particular people as vertices and some other sets. If some pilots were considered, certain pilots will be considered like that one in one set. The other set who can be flown, they can fly with together. Or in this case, these boys and girls, they can dance together. These are cases of assigning something to something. That is means, since these problems are matching or assignment, now when considering to graph theory, we are just putting it as points. And it's one set of vertices to another. And now we will see what is the formal definition of matching. Let G be a PQ graph. Means G is a PQ graph means G has P vertices and Q edges. Or it is of order P and size Q. G be a PQ graph and M a subset of edge set of G. It is said to be a matching if all the elements of M are elements in G. That means M is merely a subset of edge set of G. And no two elements are adjacent in G. No two elements of M are adjacent in G. Means if we are taking let G be a graph, how this? It's one simple graph, right? And we are taking this, if I am taking this edge E1, E2, E3, E4, we have already seen that this E1 is adjacent to E2. E2 is adjacent to E1 and E3. Thus, E1 is adjacent to E2 and E4. How? Two edges are said to be adjacent if they have vertex in common. And M is said to be a matching. That is, some subset of edges of G is said to be a matching if no two elements of M are adjacent in G. That is, that if we are taking this E1, then E3 only can be taken from this set. Then this E3 and E1 and E3 forms a matching in G. Okay. Obviously, we can say that every single edge is a matching in a graph. Why? Because it's not adjacent to anything. We are taking single edge and it is obviously a matching. Now a matching in a graph can also be defined as set of edges with the property that no vertex is incident with more than one edge in the set. How? In considering this case, here we are saying that if it is V1, V2, V3 and V4, we were considering this matching, if we are considering this matching E2 and E4, then we can say that which all vertices are incident with this V1 and V4 is incident with only one edge. Also V2 and V3 is incident with only one edge. Suppose we are considering this E1, E2, E3. Okay, then these vertices V2 is incident with E1 and V2 is incident with E2. That is the case here. We are saying that a matching in a graph can also be defined as set of edges with the property that no vertex is incident with more than one edge in the set. That is, if we are considering here E1, E2, E3, will it form a matching? No. Because we can see that this V2 is incident with both E1 and E2. Okay. The matching, that is once again saying that a matching in a graph can also be defined as set of edges with the property that no vertex is incident with more than one edge in the set. And we have already defined matching to be the set of edges which are non-adjacent in G. Okay, it is a subset of edges which are non-adjacent because they don't have any vertex in common. Or it can be said that a set of edges in which no vertex is incident with more than one edge. A matching set, next concept is maximal matching. Matching M is said to be a maximal matching. We all know what is condition. There exists no other matching M dash which properly contains M. That means maximal means it is to be at the maximal limit. No other matching can contain that matching. Okay, we will see the examples later. In K3 means complete graph on 3 vertices. It is just simple like that. What? 3 vertices are, okay, it's K3. K3, a single edge is a maximal matching. Can we, because if we are taking this edge, can we add this edge or this edge to make a matching? No, it won't be a matching. Only this edge itself is a matching. And it is also a maximal matching because no other matching can contain this edge itself. Okay. The edges drawn with heavy lines and these two figures are also cases of two maximal matching. Consider this here. If I am taking this edge, can I take any other 4 edges? No. Why? Because this edge is incident to this, adjacent to this edge, and this edge is also adjacent to this one. This edge is also adjacent to this one. This edge is also adjacent to this one. So this is the case of only one maximal matching in this graph. Okay. Now consider this graph. Same representation of the same graph. But here, if I am taking this edge, I can take this edge also. Considering this single edge itself is a matching. And a single edge in a graph constitutes a matching. But I am taking this edge. It's a matching. Can I take this edge then? No. This edge also I can't take. This edge also it is not possible. I am taking this edge. It's okay. If I am taking this edge is also okay. This matching. Two maximal matching, because will there be any other matching we can consider containing this E1 and E4? E1, E2, sorry, if it can be named E3 and E4. If I am taking this E1 and E3, does there exist any other matching? Which contains this E1 and E3? No, we cannot find any other matching. Also, if it is this E5, and here also we are taking it as E5. We cannot take any other matching in this graph G1 containing this edge. Similarly, we cannot take any other matching in this graph containing these two edges. So it is the cases of maximal matching. Okay, clearly. So another thing, I can take this E4 and E2. It is also another maximal matching. Okay. Not two edges are adjacent. Or we can find that vertices such that one vertex is incident only with one edge. Clearly, a graph may have many different maximal matchings of different sizes. Here we have the same case. That is why I have drawn the same graph here. Here we have two maximal matchings and here we have only one maximal matching. Clearly, a graph may have many different maximal matchings and of different sizes. Among the maximal matching, we have seen here graph has many different maximal matching. That may be of different sizes. Okay. Among the maximal matchings, one with largest number of edges is called largest maximal matching or maximum matching. Okay. Considering here, we have this maximal matching as 1. The cardinality of this maximal matching is 1 here. Whereas the cardinality of this maximal matching is 2. The maximal matching which with largest cardinality is termed to be the maximum matching. That is largest number of edges. Matching with largest number of edges or can be told as largest cardinality. That is called largest maximal matching or maximum matching in a graph. Thus, M is said to be a maximum matching if there exists no other M dash, such that cardinality of M dash is greater than M. So here, once again, it's saying that if we are taking this same graph, we can, for a graph, we may have different matchings and different maximal matchings. And of the maximal matchings, the matching with largest cardinality is termed to be the maximum matching. Matching, maximal matching and maximum matching. Okay. Maximal matching having the largest cardinality is referred to the maximum matching or largest maximal matching. You can use either terminology. The number of edges in a maximum matching, that is largest maximal matching, is called the matching number of a graph. Here in this graph, the matching number of this graph is 2. That is the cardinality of the maximum matching is termed as matching number of a graph. Okay. So what is the matching number of K3? It's 1. Now consider these examples. Here it is a graph G. G is a disconnected graph. Right? Why G is disconnected? Because between these portions, these two portions, we cannot have any path between these two set of vertices, right? This is a disconnected component, graph with 2 components, and this is a single graph with 1 component. And for containing this, look at the first component. Sorry, graph G. Look at the first graph G with 2 components. Here we can see that E2 and E4 is a maximal matching. Can we find any other matching containing this E2 and E4? It's not possible because if we are taking E1, because E1 is adjacent to E2. Taking E3, E3 is adjacent to E2. Considering E5, E5 is adjacent to E4. So if we are taking this E2 and E4, it is a maximal matching. Okay. I can find another maximal matching also. E1, E3, E5. Because none of them are adjacent. E1, E3, E4, it is also a maximal matching. Okay. And this maximal matching E1, E3, E4 or E1, E3, E5. These maximal matchings with maximum number of edges in it. So it is called the maximum matching. Maximal matching with maximum number of edges is called maximum matching. Okay. Here, what about this edge? Here we are taking, if this x2 and x4 is taken, it's a maximal matching as well as maximum matching. Okay. Just if you take few seconds to digest the terminologies, maximal and maximum. Maximal means we cannot add any other edges to that side. So that if we are adding any other edges to that, the matching property will be lost. That is, the condition of matching is lost. And the maximal matching with maximum number of edges, that is the largest number of edges, is termed to be the maximum matching. Now what we are saying, that when an edge is said to be matched under M, an edge EG is said to be matched under M, or you can say that E is not unmatched under M. If condition E is matched under M, if E element of M, and if E is not an element of M, then we say that E is unmatched. Here, when considering this, when we are saying this E to E4, then E to E4 is matched under M. That is E2 and E4. These edges are coming in this matching. So they are matched under M. If M equal to E2, E4, then we say that E2 and E4 is matched under M. This E1, E3, E5 is unmatched under that M. Because we are always saying that M is a subset of edge set of G. So this M means E2, E4. Okay. If you are taking this E1, E3 and E5, that is M. Then E1, E2 and E4 is unmatched under that M. Okay. Then edge E element of EG is said to be matched or unmatched. How? If E is element of M, then it is said to be matched under M. If it's not an element of M, it is said to be unmatched. Okay. A match, then on some remarks are there. A matching M is said to be maximal if every edge not in M is incident to an edge already in M. We have seen what is a maximal matching. That is, we cannot add any more edges or no other matching. We cannot add any more edges to that matching. So as to that a subset of edges remain matched. If matching is said to be maximal, those edges which are not in M, that is those edges in G which are not M, is adjacent, is incident to only one edge, that is, or incident to an edge, that is, or we can say that a matching in M is maximal if every edge not in M is incident to an edge already in M. Okay. Every maximum matching is a maximal matching. Every maximum matching is a maximal matching, but the converse need not true, because every maximal matching need not be a maximal matching. Here, we can see that E2 and E4 are maximal matching. Are they this maximum matching? No. Because we can find another with the largest cardinality, E1, E3 and E4, or even E3, E4. Okay. So, this E2, E4 is a maximal matching but not a maximum matching. But a maximum matching is always a maximal matching. Okay. That is, first we have seen what is a matching. Matching is a subset of edges which are non-adjacent. Then we have seen what matching are this maximum matching. Maximum matching is we cannot add any more edges to that. So, if we are given a matching and if we are able to add, that is if M is said to be a maximum matching, if there exists no other matching M dash which contains this M. And maximum matching is the largest maximal matching. That is, maximal matching having the largest cardinality is said to be the largest maximal matching or maximum matching. And an edge is said to be matched under M if it belongs to that matching, else it is said to be unmatched. Then we call this matching maximal matching. If a matching is maximal, if every edge not in M is incident to an edge already in, okay, then every maximum matching is also a maximal matching. That is, maximal means it is maximum. Maximum means it is maximal. But maximal does not imply it is maximum. That is to show that maximal matching need not be maximum matching. Now consider this P4. We are not familiar with the P4. P4 means a path with 4 vertices, and now P6. Just if I am taking this P4, I can take 2 different matchings. Okay, these middle edges. Also consider this P6 also. It's also if we are considering the middle edges. This is the maximal matching in this. Heavy lines are maximal matchings in these 2 graphs. Okay. Are they maximum? No. Because why it is maximal matching? We cannot add any more edges to this. If I am considering this edge in this one, can I add any more edge to this matching? No. It is a maximal matching. But I can take another matching also which is maximal considering the end edges. If I am taking this here, end edges here and here. I can have two edges in that matching. It is also a maximal matching. So when getting to the concept of maximum matching, this maximum matching is this one, considering these end edges. Here also if I am considering this end edge, then I can I will be getting 3 edges. Okay. So that maximum matching with maximum number of edges 3. So it is the maximum matching. So what is the maximum matching? It's with 3. Here it is 3. Maximal matching is also 3. But here when we are considering the middle edges, it is also a maximal matching, but it is not at all a maximum matching. Okay. Once again, if we are considering the middle edges, we cannot add more edges as the middle edges constitute the maximal matching. Okay. Because middle edges constitute the maximal matching. But when we are taking end edges, constitute the larger maximal matching, and thus we getting a maximum matching. Okay. This maximal matching, and then it is maximum matching. Maximal matching with the largest number of edges is termed to be a maximum matching. Now we will see when a vertex is said to be saturated with respect to a matching. A vertex V is said to be saturated by a matching M, or M saturated, or a matched vertex with respect to M if V is incident with an edge in M. That is, if we are considering this graph, and this, if we are considering this edge E, and if you are considering this V1, V2, V3, V4, and if you are considering this edge matching this E only, then this V2 and V3 is said to be matched under that matching, or saturated with respect to that matching E. And V1 and V2 are unsaturated vertices, or unmatched vertices, or simple vertex with respect to M. Okay. Now going to another example. Consider the matching here. Here we are given a graph with 5 vertices, V1, V2, V3, V4 and V5. Okay. And now considering this X2, X4. Is it a maximal matching or maximum matching? Is it maximal? Yeah, of course, it is maximal. Why? Because we cannot add any more edge or no other matching there exists which contains this X2 and X4. We cannot find any more matching M dash which containing this X2, X4. So it is maximal matching. And consider another matching. I want to take, if I am going to take this X5, then which all edges I can take? Can I take this or this? No, because they are adjacent to this. Those X3 and X4 cannot be taken. If I am taking this X5, I have the possibility to take only X2 or X1. So this case, here the matching number of this graph is just 2. This maximal matching is 2. Here, if we are taking this X2 and X5, it is maximum as well as if you are considering this X2 and X5, it is maximal matching. Also, it is a maximum matching. So the vertices which all are matched under this matching, because we are taking this X2 and X5. So which all edges are matched? Sorry, which all vertices are matched? V1 is incident and V1 and V2 incident with this X2. So V1 and V2 is matched. And comparing to this X5, this V2 and V5 is matched. Only vertex which is not matched under this matching E2, E5 is V4. So it is also called as unmatched vertex under this matching, which is equal to X2, X5. Or we can say that V4 is a single vertex with respect to M. Okay. Matched vertex, unmatched vertex. Unmatched vertex is also termed to be single vertex with respect to that matching. Now we are going to see what is an M alternating path. If we are given a matching, then what is that M alternating path? Path means a walk. We have seen what is a path. Path is an alternating sequence of vertices and edges starting with vertex and ending with vertex, and in which this no vertex repeats more than once. Okay. An M alternating path means when vertices are not repeating again, obviously the edges won't be repeating. So then M alternating path is a path whose edges are alternatively matched and unmatched under M. That is, if you are given a matching, that is, matching means set of edges. And M alternating path means whose edges are alternatively matched and unmatched. We have seen what is matched and unmatched. So that if one edge is there in matching, the next edge will not be there. Then other will be there in matching. So if we are taking this graph, here we have vertices U1 to U6 and edges V1 to V6. Sorry, E1 to E6. Vertices from U1 to U6 and edges from E1 to E6. And we consider one matching E2, E5. Where is this E2 and E5? Okay. Now what we can say about this E2 and E5? Are they maximal or anything else? It is a maximal matching. Okay. Why? Because can we find any other matching that is containing this E2 and E5? If we can add this can we add this E3? No. Because E1, E3, E5 are adjacent. What about this E4? When we are considering this E2, E4 and E5, this E4 is adjacent to E5. So we cannot add this E4 here. And also we cannot add this E1 to that. So this is a maximal matching. And then we can, if this path, we are considering another path U2, E2, U3. Now consider this path E2, E2, U3, E3, U4, E5, U5. Here we can see that this E3 is not matched. E3 is not under this matching. That is, M alternating path is a path whose edges are alternatively matched and unmatched under M. We have seen how an edge is said to be matched under M. A vertex is matched under M. Okay. So here we are saying that this one edge is not. If one edge is there in matching, the next edge will not be there in matching. Such a path that goes on is called an M alternating path. Okay. And then we will see that what is M augmenting path. A non-trivial path that begins and ends with an unsaturated vertex. That is a non-trivial path. That means there exists a path. Non-trivial means, now we will see what is M augmenting path. A non-trivial path that begins and ends with an unsaturated vertices in M is called an M augmenting path. We are always saying that when we are considering a matching, then we are considering the edges and vertices which are, whether they are matched or unmatched, but with respect to that particular matching only. Okay. When we are saying that this M augmenting path means it starts with a vertex which is unsaturated. That means it is not an endpoint of any of the edges in the given matching. So if you are considering this matching M equal to E2, E5, and then M augmenting path means it starts with a vertex which is unsaturated. So here if you are starting with this U2, it is a saturated vertex, because why? U2 is incident with this edge E2 which is a part of this matching. So you cannot start with it. We have to start either with this U1. Then U1, E1, U2, E2. Then this one, U3, E3, U4, E5, U5, E6, and ending with unsaturated vertex U6. That is a path which starts and ends with an unsaturated vertex. That is, a vertex is said to be unsaturated with respect to a matching. What is the condition? A vertex is said to be unsaturated with respect to a matching if it is not incident with an edge in the matching, or it is said to be also a single vertex. So if we are starting and ending with an unsaturated vertex, then it is said to be an M augmenting path. Okay. This is what is an M alternating path means, whose edges are alternatively matched and unmatched by the M. There we are considering with the matching of edge, whether it is matched or unmatched. And this M augmenting path means it starts and ends with unsaturated vertices. So obviously it comes on second edge, that first edge that comes in this path will be unsaturated, unmatched edge will be. And also the ending edge also will be unmatched edge. Okay. So what is M alternating path and M augmenting path? Hope it is okay. Now we'll see what is a perfect matching. What is a perfect matching? A matching is said to be a perfect matching if all the vertices of G are saturated by M. What is saturation? It is contained in that M. A matching M is said to be perfect matching if all the vertices are saturated by M. Now we are considering this E1, E3, E6. E1, E3, E6. So, consider this E1, E3, E6. We can find that this U1 and U2 is incident with this edge E1. Also, U3 and U4 are incident with the edge E3. And this U5 and U6 are incident with the edge E6. So, all the vertices, a vertex is said to be saturated or M saturated means if it is an endpoint of any of the edges in that matching. And here we see that all the vertices of this graph are saturated with this matching. That is, every vertex is endpoint of any of the edge in G. Every vertex is endpoint with any of the edges in this G. Okay, so every vertices are saturated under this matching E1, E3, E6. E1, E3, E6 is a maximal matching, and also a maximum matching, and also this saturates all the vertices of the graph. So this matching is said to be a perfect matching. Okay, matching, maximal matching. Then we have seen what is a saturation, where when an edge is said to be saturated with respect to a matching, that is, if edge E belongs to the matching, then we say that edge E is saturated with respect to that matching. Also, vertex is said to be saturated if it belongs to that, if it is an endpoint of any of the edges in matching. If every vertices are saturated, then it is termed to be a perfect matching. That is, a matching M in a graph G is said to be a perfect matching if all the vertices of G are saturated by M. A perfect matching must be a maximum matching. Do you have any doubt in that? I hope no way. Because whenever a perfect matching is happening, it is a maximum matching also. If a graph has a perfect matching, obviously the cardinality of the vertex set must be even. What will be happening if it is odd? That is, if I am there considering this. Can I have any perfect matching of this graph? No way, because if I can consider all of these two edges. That means if I am considering these edges E2, E3, can I completely put all the vertices here? No way. So when a graph has perfect matching, the cardinality of the vertex set is always even. That is, modulus of Vg must be even, or cardinality of vertex set of G is even. Now we consider this example. This graph with vertices A, B, C, D, and which are the edges AB, BC, BD and CD. Okay. If I am considering this BC itself, a single edge is a matching, because we have from the very first definition of matching, we have seen that every single edge is obviously a matching. Now we have seen some more terminologies like saturation and all. This BC, which are BC, the edge BC, which all edges are being saturated under this BC. These vertices B and C are saturated, whereas A nor D is not saturated. Okay, you can now consider the set of edges BC and BD, which are all there. This one, BC, BD. Do they form a matching? No, because why? These are adjacent edges. Also, these have a common vertex. This is the condition that matching set of edges is said to be matching. Only one vertex is incident with maximum one edge. Here, the vertex B is incident with two edges. So, it is not a matching. And what about this AB and CD? And we are considering these edges matching with these two edges, AB and CD. It's a matching. It's a maximum matching. Maximal matching. Then it's also a maximal matching. Sorry. When considering these edges AB and CD, it is a maximal matching. Also, it is a maximum matching. It's also a perfect matching. Why perfect matching? It saturates all the four vertices. Because here, if all the vertices of given graph G are saturated under a given matching, then it is said to be a perfect matching. What means a vertices are said to be saturated? If every vertex is an endpoint of an edge in the matching, then the vertex is said to be saturated under matching if it is an endpoint of any of the edges of that matching. If all the vertices are saturated, then it is termed to be all the vertices of a given graph G are saturated. Then the given matching is termed to be a perfect matching. Okay. So here, this matching concept, I hope it is okay with you all. Now we have seen what is maximal matching and maximum matching and all. Actually, the characterization of maximum matching in a graph was given by Birch in 1957. Now we will see what is the statement of Birch theorem. A matching M in a graph G is a maximum matching if and only if there exists no M augmenting path. What is this M augmenting path we have seen? And what is this maximum matching we have seen? That is, the theorem states that if G has a maximum matching, then there exists no M augmenting path. If G, conversely, that is if and only if means, if G has a maximum matching, then there exists no M augmenting path. Only if condition means if G has no M augmenting path, then G has a maximum matching. Okay. Here we can see. Consider this matching. here we have already seen that E1, E3, E6 is a maximum matching. No doubt with that. Why? E1, E3, E6, we cannot find any other matchings that containing that. It is a maximal matching, and the cardinality of the maximal matching which is with the highest is this one, 3, and so it is also a maximum matching. And what is that condition with the M augmenting path? It starts with a matched vertex, and M augmenting path means a path consisting of matched and unmatched edges. Or if there is one matched edge, then next edge will be unmatched edge. We cannot find an M augmenting path with this. Okay. Suppose we have an M augmenting path. We have already seen that this graph has one augmenting path like this, which with respect to S another matching. Which one? When we are considering this E2, E5, we can find one M augmenting path. Why? Which one? Consider this example. Okay. Here we have on maximum matching like this E1, E2, E1, E3, E6. Then what is the definition of M augmenting path? It's a It is a path starting and ending with unsaturated vertices. Okay. So here we cannot find any such path like that. If we are considering this E1, E3 and E6, can we find any vertex which is not saturated with any of these edges? No, we cannot find any such augmenting path. Then, if we have seen that with respect to this graph, already we have seen in that we have on M augmenting path. With what is we have seen one augmenting path like U1, E1, U2, E2, U3, E3, U4, U5, E6, U6. But with respect to which matching we had found this M augmenting path, it was with respect to E2, E5. Is it a maximal matching? It is not a maximal matching, also not a maximum matching. Okay, because we have in this graph, the maximum matching is this one. So with respect to this, we cannot find an M augmenting path, nor if a graph has M augmenting path, we cannot find a maximum matching. That is what this Birch theorem states, that a matching M in a graph is maximum if and only if there exists no M augmenting path in G. Okay. Although matching is defined, we have seen so far, we have seen a graph which is a normal graph we have seen. But most properties of matching are studied in terms of bipartite graphs. What are bipartite graphs? Yeah, graph in which the vertex set is partitioned into two, V1 and V2, such that no two vertices in a particular partition is adjacent. That is, here we cannot find any edge like this, because they are adjacent only to here. Like this. That is, no two vertices in this. When we are dividing this disjoint union of vertices, then we call it as a partite set. No two vertices in a partite set are adjacent. Or we can find a particular partition of vertices of G. Then we can divide the vertices of G into two such that no two vertices in one partite set are adjacent. Such a graph is termed to be a bipartite graph. Usually these matching properties are studied extensively using bipartite graphs. So now we are going to define what is a complete matching. We have already seen different properties of matching. We have defined what is matching. Then we have seen what are the different properties of matching and all. Now we are going to see what is a complete matching. A bipartite graph having a vertex partition V1 and V2 is said to be a complete matching if all the vertices of V1 are matched to we have some vertices of V2. That is formally a bipartite graph having a partition of vertices V1 and V2, a complete matching of vertices in the set V1 into those in V2 is a matching in which there is one edge incident with every vertex in V1. That is, every vertex in V1 is matched to some vertex in V2. Then we call that it is a complete matching. So every element then matching from one side to another side. It is also, we can, it is familiar like our function. Every element in first side is being matched to some element in the second side. So function. Now we will see if it is okay for the complete matching. Okay. Otherwise, we say that every vertex in V1 is matched against some vertex in V2. That is the same as the concept of our function that we have already learned from our school classes. So now we will see whether it is okay or we have to impose some more restrictions on these functions, on the definition of function like this. Okay. So consider this bipartite graph with vertices x1, x2, x3, x4, and here y1, y2, y3, x4, y2, y3, y4, y5. Here it is some matching. Okay, for complete matching means a complete matching should include the edge x1, y1, x2, y3, or x because x2 here it is matched to y1 and y3. So we can have x2, y3 or x3, y3. Why? Because x3 is also being matched to pair to this y1 and y3. And x4 we can take it to y5. No problem. So this complete matching should include the edges. Which all edges we have to include? x1, y1, x2, y2 or x3, y3. If x3, y3 is included, can we put this x2, y2? Because the condition of matching will be, if x2, y3 is included, then we cannot put this x3. Because why? x3 is matched to y2. But then if we are putting that, then the condition of matching will be lost. Because these two have common end. So, likewise, if x3, y3 is included, we cannot put this x2. We cannot put match x2. So, now we found it to be a function like this. Now, can we say that it is a function like that? No. So, consider this matching here. Here we can match 1 to 5, 1, 2, 3, 4. And here I have put like this 5, 6, 7, 8, 9, 10. So, here I can take this, with which all vertices here, this vertex 1 is matched. It is matched, it is being related to 5, 8 and 10. And 2 is related to 6 and 7. And 3 here we can find to 5, 7 and 8. 4 is related to 9. That's direct because here we can take this 1 to 5, 2 to 7, 3 to 8, 4 to 9. We can take everyone independently. It's a case of complete matching. So how do you feel? Can you relate to something to our things that we have learned earlier? Yeah, it's a function which is 1, 1. Okay. A complete matching. In every graph, a complete matching may not exist. If a complete graph, complete matching exists, this is the largest maximal matching. If a largest maximal matching exists, does not mean that a complete matching exists. But if a complete matching is existing, it will be the largest maximal matching. For instance, the complete matching of a set V1 into V2. We must have vertices, as many vertices in V2 that as much in V1. Okay. Now we will see real life situation example. Suppose there are some job applicants and some vacant positions. Job applicants and positions. There must be at least, to grab all the applicants, we must have at least as many positions. Whether if there are 10 applicants and only 5 positions are available, can we grab all these 10? No. There must be at least 10 positions available to grab all these 5. Is that condition sufficient? We will see. Suppose there are 4 applicants, A1, A2, A3, A4. And we are available to fill the positions. Positions I have given us P1, P2, P3, P4, P5 and P6. Suppose that normally we can see that there are 4 applicants only and 6 positions. Yeah, this 4 can be grabbed. 4 can be hired. But if it comes to some particular situations like this, if applicant A1 is qualified to fill these positions P2 and P5. Also this A2 is qualified to fill only this P2 and P5. And A3 can be used to fill this P1, P2, P3, P4 and P6. Okay. But A4 is qualified to fill only P2 or P5. So can be grabbed by, even though they have 6 positions and only 4 applicants, is it possible to hire all the 4 applicants and assign each a suitable job to his position? We'll see, put the situation to a bipartite graph. Okay, where the applicants and the positions and this how they can be filled. This A1 can be put to P2 and P5. Similarly, A2 to P2 and P5. This A3 can be put to all other many positions and A4 also P2 and P5. So, here, although there are 6 positions, can I take this A1, A2 and A4? Because only 2 can be put. Why? Because both the 3 are qualified to fill only the 2 positions P2 or P5. So, in this case, I can take only 2 positions, 2 people. Therefore, one cannot be matched. This in turn leads to another necessary condition for the existence of a complete matching. Every subset of R vertices in V1 must be connectively adjacent to at least R vertices in V2, where R value of R changes from 1 to 3 to maximum cardinality of V. Here, the cardinality of R was there. The cardinality of V1 was 4 and cardinality of R was 3. I can vary from 1 to the maximum cardinality. If all the 4 were considered to be fit for the positions P2 and P5, can I take all the 4? No. There only 2 can be taken. Only 2 could have been taken. Okay. So, and the necessary condition for complete matching is that for R subset of vertices in V1, they should be collectively. They should have at least R vertices in R. Common. They should be common in relation with R vertices in V2. Now we will see problem of distinct representatives. Some senators S1, S2, S3, S4 and S5 have it. And some 3 committees C1, C2, C3 and how they are related. The senators are being put to these committees. The membership is shown in this bipartite graph. One member from each committee to be represented to a super committee. That is, if I am taking a member from this C1, one member out of this C1 has 2 members, C3 has 3 members, and C2 has 3 members. C1, 2 members, 3. Is it possible to convert this? Can I put them in different form? So is it possible to select distinct representative to a super committee? Yeah, here we can take it. How we can take it? I can take this C1, from the C1, I can take this S2. And from C2, I can take this S1. And from here, I can take this one. Or another combinations are also possible. Okay. This is a case. So, the problem of distinct representative, this problem known as problem of distinct representatives. It was first formulated and studied by English mathematician Philip Hall in 1935. The problem is of finding a complete matching of V1 to V2. And here it is possible. And in this case, it's a case of complete matching. Hall's theorem. Then Hall has formulated a theorem. What is that? A complete matching from a vertex V1 to V2 in a bipartite graph exists if and only if every R subset of R vertices in V1 is collectively adjacent to R or more vertices in V2 for all values of R. First, we have seen that R vertices should be collectively adjacent to at least R. Here, Hall has given a condition that it should be collectively adjacent to R or more vertices in V2 for all values of R for the existence of a complete matching of a subset, two set of vertices V1 and V2 of a graph G. And now we can see the consequence of the Hall's theorem. In a bipartite graph, a complete matching from V1 to V2 exists if and only if there exists a positive integer m for which the given condition is satisfied. The degree of every vertex in V1 should be greater than or equal to m. And for this, m should be greater than or equal to every distant vertices in V2. If degree of every vertex for a positive integer m is there, if degree of every vertex is greater than or equal to that particular value and the degree of every vertices in this V2 is less, that is m is greater than, or degree of every vertex in V2 is less than that m, then this complete matching is possible. Now we will see the next condition. That is consequence of Hall's theorem. It should be clear that there exists a complete matching from a vertex V1 to V2 happens if we can take a positive integer m for which the following condition, that is the degree of every vertex in V1 should be greater than or equal to m, and this m should be greater than or equal to the degree of every vertex in V2. Another consequence of Hall's first condition was that Hall's theorem is that Hall's marriage theorem. It answers this question. If there are a finite set of girls, each of whom knows several boys, and under what condition that all the girls may marry the boys in such a way that each girl marries a boy whom she knows. Okay. We can formulate that condition in a graph theoretic situation like this. Suppose there are 4 girls and 5 boys. And suppose the friendship can be shown like that. That is, G1 knows B1, B4 and B5. And the girl G2 knows only B1. And G3 knows B2, B3 and B4. And G4 knows B2 and B5. So can be formulated such a condition that each girl marries the boy that she knows. Now it is possible that we can put here G2 can marry only B1. Others have many options. So G2 can marry B1. And then G1 can marry B4. G2 can marry B3 and G4 to marry B2. This is a complete case of matching from V1 to V2. Here I can put, instead of G1 to going for B1, B4 I can select another persons also. It can be selected to B5 also. G1 can be married to B5. So different cases are there, but this particular case is one solution for this case. Okay, you can find different cases also from this case. Immediate consequence of Hall's marriage theorem is the necessary and sufficient condition for the solution of a marriage problem is that K girls should collectively know at least K boys. For this K is where K lies between 1 and m, where m is the maximum number of girls. Okay, we have already seen this Hall's condition. Complete matching. Okay, what is the condition for existence of complete matching? And now the consequence of Hall's theorem also states the same thing. They should be collectively known to at least, if K persons should collectively know at least K persons in the other side. Now, another condition, what is that? If let G be a bipartite graph with vertices V1 and V2. For each set A of V1, Let phi of A be the set of vertices in V2 that are adjacent to at least one vertex in A. Okay, then a complete matching from V1 to V2 exists if and only if modulus of A less than or equal to modulus of phi of A for each subset of A. For each subset A of which one? V1. Okay. Let G be a bipartite graph with vertices V1 and V2, and if A is a subset of V1, then we can find a subset phi of A in V2, such that modulus of A should be less than or equal to modulus of phi of A. Then we say that a complete matching exists. But determine the necessary and sufficient condition for a complete bipartite graph Kmn to have a perfect matching. What is complete bipartite graph? If every vertices in one partite set is adjacent to every other vertices in the other partite set. That is, means if here we have 2 vertices and here we have 3 vertices, these 2 vertices should be adjacent to all the 3 vertices in the other set. Then we can say that it is K 2, 3. And in the same way, it is when this 2 and 3 are extended, can get this Kmn. What is the condition for what is perfect matching? If every vertices are saturated. And what is complete condition to have? What is the condition to necessary and sufficient condition for a complete bipartite graph to have a perfect matching? That is, every vertices are being saturated. It happens only when m equal to n. Okay. What is the condition for this matching and all? I have already told, because now 2 vertices should come as an end of any 2 of the edges, or no 2 edges are adjacent. For this condition is m equal to n. Okay, that first we can see this proof like this. Assume that it is m equal to n, then V1 and V2 have this same set and this matching. Directly U1 V1, U2 V2, etc. UM VM is a perfect matching. Suppose if the graph has a perfect matching and suppose less with one set has less cardinality. Since every vertices in V1 has to be matched to this V2, at least one cannot be matched. There must be at least this m vertices should be matched to at least this one. And if this m is less than V2, some vertices in V2 would not be a part of the edges. So these remaining vertices in V2 will be left and they won't be get matched. And so it cannot be a perfect matching. So for the condition of Kmn to be the perfect matching is m should be equal to n. Now the condition whether this graph, what about this condition? This graph has a complete matching. Yeah, this graph has vertices A, B, C to D, A, B, C, D, E, and here I have written a small letters E to F, A to F. This graph has 2 types of, there exist 2 complete matchings. And this one is the first complete matching and this one is another complete matching. And can we find any matching from V2 to V1? No, it is not possible. Why? Because the cardinality of V2 is higher than V1. So we cannot find a complete matching from here to here by following the Hall's condition and what are the conditions that we have discussed so far. Now matching and adjacency matrix. We have seen what is an adjacency matrix of a graph. We can find the complete matching of a graph easily with respect to the adjacency matrix. And the adjacency matrix of a bipartite graph is given like this. As xg, where a V1 and V2 are the set of vertices and n1 and n2 are the cardinalities of V1 and V2, such that the graph has total cardinality of n. Then the adjacency matrix of G can be represented like this: xg equal to 0, x12 and x12 transpose 0. It will be like this. Actually, it can be put like this. It's a square matrix, it's a square matrix, and it's a square matrix. But the x12 is an n1 by n2 matrix containing the information as to which n1 vertices of V1 is adjacent to how these n2 vertices of V2. Okay, then x12 transpose means the transpose of x12. Now we will see this graph. The complete matching of this graph can be found. We have already seen how we have By searching through this and all, we have found how to find the complete matching. Now consider the graph. Same graph. How we can find this complete matching? For that, first we have to write the adjacency matrix like this. First, x12, how we can write? This, here we are taking this A, B, C, D, E and a small a, B, C, D, E, F. And we are writing that like that. That A is adjacent to B and F. Here, A is adjacent to B and F. Also, B is adjacent only to B. That is by consider this second row. B is adjacent only to B. And C is adjacent to C and E here. Right? C, E. They're like that. D is adjacent to D only. And E is adjacent to A and D and A. Like that. Okay. This matrix I have put like this. That is x12. Instead of putting x12, I have clearly expressed it like this. X n1 by n2 matrix. Here we have n1 as 5 and n2 as 6. So 5 by 6 matrix here. And x12 is here. Okay. And the transpose of this is okay. Now how to find this complete matching? From here we can see that from this row. Here B is first only one non-containing the row. First row is that B. So then B is containing this. Choose row B and column B. Since B contains only once place in the entire row. And discard that column B. And now which row is like that? Now we can choose this D. And choose this row and this column. Okay. First we have removed this column B and now we are choosing this. Now I can think we can take which row has the ones only one. Now we can take this column E. Because why? Column E is with only one. So choosing this column E and row E and this one. Now I have this column is also being discarded. Now I can take this row A and discard this F. Okay. Now I am left with C. And I have two columns. I can take either this column C or column E. Okay. On each step, after each steps, I can go like that. So after the first step, because if I am removing after the first step, I'll be left with the matrix with A with after C, because that B has been removed. So A, C, D, E, and that column will be B is removed. A, C, D, E, F. Like that. Whatever entries are here, deleting this row B and column B, I have to put on that. And continuingly, we will get the final matrix like this. Okay. The final matrix will be like this, and this is the final complete matching of the graph. Earlier, we could find the complete matching like this because the graph was so simple. So if it is so complicated and all, we can put the matrix like this. That is, X can be put like this. Adjacency matrix can be put like this. And this, on simplifying this graph matrix, simple matrix, we can find the complete matching from one set of vertices to another set of vertices. Here, whether we can see these two graphs are complete matchings from V1 to V2. Here we can see that three vertices are simultaneously matched to two vertices. V1, V2, V3 are simultaneously matched only to or collectively matched only to the vertices A1 and A2. Okay. So it is by Hall's theorem, we cannot find a complete matching from V1 to V2. Now we will revise what all things we have discussed so far in this session of matching. Matching we have discussed, then maximal matching. Maximum matching. Matching means set of edges which are non-adjacent in G, and maximal matching means we can find no other matching M is said to be a maximal matching if we cannot find any other matching M dash such which contains this M. And maximal matching is The largest maximal matching is said to be a maximum matching. And saturated vertex with respect to matching means if it is an endpoint of that vertex is an endpoint of a edge in matching. Also, an edge is said to be saturated under M if it belongs to M. And we have seen what is M alternating path, and we have seen what is a perfect matching. A perfect matching is matching in which all the vertices are saturated under a matching. Then the matching is termed to be a perfect matching. Then we have seen what is Birch theorem and complete matching, and Hall's theorem for the existence of complete matching. I hope you all enjoyed this session of graph theory where we discussed matching. And thank you for watching. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.